2 recordings for this one lecture. Okay. So now we're getting into the reactions part. And I think what I was talking about before was that we learned about just the basics of the reactions, which means that you had the substitution, elimination, rearrangement, and then addition reactions. Okay, so those are the 4 classification of reactions that we did. Just starting off. So in this chapter, we will have 3 different kinds of reactions. Okay, so we will do substitution reactions, we will do elimination reactions, and then we will do rearrangements. Okay, so 3 of them are in this chapter. Addition is in the next one. Okay, so we'll start with SN2 reaction first, and that's a substitution reaction. Okay. And again, just let me know if you can't hear me at any point. I may just have to keep going in and out today. I have another device, but it doesn't write as well. Okay. Talking about SN2 reactions. So here what we have is a substrate. And this is not writing properly, so I can tell that the computer is not feeling well. So first of all, you have to be able to identify all of these different components, okay, of a reaction. So here is the substrate. Here is the nucleophile. And we learned about the nucleophile that you can just, take a shorthand for that and U minus. And then we have the product. And then here is the leaving group. Which you can call LG if you want to as the leaving group. So this is a substitution reaction where you're substituting chlorine for hydroxide. Now in this reaction is chlorine for hydroxide, and another reaction it could be something else. Okay, so in order to understand how this reaction is working, you need to understand the mechanism of the reaction, which means, are you breaking the Cl bond first, okay, for the leaving group to go away, and then the OH is going to attach here? Or is the OH going to come here first and then have the chlorine leave? What is going on? Okay, to understand that, you have to do kinetics. Okay, and the kinetics is studying the order of reaction. And so here it turns out that the rate is equal to K, the substrate, and the nucleophile. So this is the rate of equation for this reaction, which means that it's a second order reaction. It is first order with respect to the substrate, and it is also first order with respect to the nucleophile. So one of the things that I mentioned to you about doing the order of reaction was to figure out the mechanism of the reaction. Okay, so now let me talk a little bit to you about the graph, okay, that we drew out before. So there is this kind of graph, and don't draw this one, the second one, and you can have this kind of graph. Okay, so in the first one, we know this is exothermic, okay, because the product energy is lower. That's not the important part. The important part is that you have only one curve, okay, on the graph. There's only one peak on the graph over here. And if you remember also, I mentioned to you, this is called the transition state. And you know that too. I don't have to tell you that. So this is called the transition state. So the link between the mechanism of the reaction, the order of reaction, and the graph, all of these 3 things are connected together. And the way they are connected is it'll tell you how the reaction is progressing. So what this tells us is that the order of reaction is second order. It is first order with respect to the substrate and the nucleophile. It means both of these things are involved in the transition state. Okay, so for the transition state to happen, both of them have to be involved in there. The other things it tells you, the graph tells you that you only have one transition state, as opposed to this graph on the right, which has two transition states. What this means is that the entire reaction is happening in one step. When we talk about the kinetics of any reaction, we talk about the slow step and the fast step. In this case, there is just one step, and that is the slowest one. And this activation energy here, this is it. This is the slowest step. After that slow step is done, boom, you have your product. That's it. Because after that, it's all downhill. Okay? Unlike here, in which you have two transition states, and so the reaction has to come down in energy, then go higher in energy again. Okay? So there are a lot of things that are connected together when we talk about the mechanism of this reaction. All right? So first of all, again, second order reaction, first order with respect to substrate, first order with respect to nucleophile. So it means both the substrate and the nucleophile are part of the transition state, which means what? It means that the bond breaking and the bond making is happening at the same time. Okay, so right now we have two different things, but in the transition state, we only have one thing. So we have to figure out a mechanism that will have only that one thing in there. So how does that work? So clear that out. Okay. So here is this reaction again. Cl minus. And so when we look at this reaction, we say what's really happening is that the oxygen, again, not the hydrogen, because oxygen is the one with the negative charge. So the oxygen here is going to attack this carbon, and this chlorine is going to leave. So there are a few things to understand over here, okay? And this is the reason why you did the nucleophile and the electrophile back in chapter 6, okay? So when you look at something like this, like a halide, you know that chlorine is more electronegative, and then this carbon is more electropositive. So first of all, this is the positive center. The oxygen here is the negative one. So if you have this as negative, a negative will not go to the negative. A negative will go only to the positive. So a nucleophile is going to be attracted to the electrophile. So this is the mechanism that's going to happen. And then as soon as you have that, what do you form? You form something like this, where you have the OH that's trying to form a bond with the carbon. Well, if it is trying to form a bond, you can't really have more than 5 bonds, because don't forget, there's still 2 hydrogens there. So it means something has to go. Now, hydrogen cannot go because the CH bond is pretty strong, but the CCl bond is weak because of the polarity of the bond. So which means that the bond that's going to break is going to be for Cl. So you write the dash lines, and you can write the dash line like this or dotted line, whatever you want to. But the dash line indicates there is some bond forming and some bond breaking happening over here. And then you put the square brackets and you put the transition state on the top. Okay, so this is what happens. And then what happens? Eventually, the chlorine is going to have to get kicked out, okay, because the OH is going to take that place. Now, we are going to have to talk about why the OH is kicking the chloride out, okay? Is that something that we have to talk about, because this is always going to happen, okay? So that's another thing, that's another discussion. But right now, that's what's happening. Is everybody okay so far? Any questions? Okay, so this transition state that we have has both the nucleophile and the substrate in it, which is why it is a second order reaction, okay? Because in the second order, you need to have both of those things in the transition state. It is what makes it bimolecular. So bimolecular means when there are 2 molecules involved in the transition state. All right, so couple of things to talk about before I get into the nitty-gritty of everything. And one of the things is that this attack that is happening here, okay? Now be careful how you draw your arrows, okay? So let me go ahead and erase this, and then I'll draw it again. So when you're drawing this arrow over here, this attack is called a backside attack. And I know it sounds horrible. It's like somebody is doing something sneaky, but it is a backside attack. That's what it's called. And where is it the backside of? It is the backside of the leaving group. Okay, so it's coming from right behind the leaving group. So once it attacks from behind, the Cl has to go from the other side. Okay, so the blue arrow that I'm going to draw now is the wrong one. Okay, that's not right. So the red one is the correct one. This is not going to happen. So when you write the mechanism for this, you have to be very clear how you're drawing the arrow. Okay, so I get very, very specific in how you're drawing the arrows in here. So make sure that it's coming from behind the chlorine, from behind the leaving group, okay, in order to do this reaction. So this is called a backside attack. So what is the importance of this backside attack? This is a very important part in SN2 reactions. By the way, SN2, substitution, nucleophilic, and 2 is for second order. So a second order nucleophilic substitution, which, I mean, when you say it, you're going backwards, but when you write it, it's SN2. Okay, so it's a second order nucleophilic substitution. So what does it mean when we say that we have a backside attack? Okay, so how does it matter to us where we write the arrow? Okay, because that's the first thing that we think about. How does it matter? Well, it matters. Okay, so here is how it matters. Let's say that you have a chiral center here. And then when you have a hydroxide, the hydroxide is going to come from behind and kick this out. Now I draw my arrow coming out of the chlorine. You can have the arrow like this also. Both arrows are fine. Okay, so if you feel like it, you can draw it on the chlorine, or if you want to be as vague as I am, it's just going out, which means it's leaving, okay, with its electrons. So this backside attack over here means that now everything is going to be inversed. Okay, so now they have OH like this, which means what happens is inversion of stereochemistry. That's what happened. And I know it's not writing properly, but this is inversion of stereochemistry. So now Cl is coming to the front, H is to the back. Okay, so this is number one priority, A, B, C. So this is going to R. Now OH is at the back, so it means that the hydrogen is coming to the front. I think what I did I flip anything? I don't know. We'll find out. Yeah, I think I flipped two things. Because this is going S, which is also R, and that cannot be R because I flipped it. Okay, hold on. I'm going to have to draw that again because it's supposed to be S. I'm going to draw it a little bit better for you. Okay, and for myself. Here. So now we have OH going to the back and H coming out. So now this is going to be S. So that is inversion of stereochemistry that happens. And it's a lot easier to see sometimes when you do cyclic compounds. Okay, so if you have a ring and you have Cl here, H here, let's say CH3 here, and H here. This is just not writing well today. Okay, I'm going to start on a new screen. Cl, H, CH3, and then H. So in layman terms, this is kind of like a cis. And then if you have a hydroxide that comes in, the hydroxide is going to come from behind and then have the Cl leave. So at that point, the CH3 on the left-hand side still remains the same because there is no change there. But on the right-hand side, things have changed now because this OH came from here and then H is on the other side, on the flip side. And so now this has become trans. All right, so it's a lot easier to see in a cyclic compound, but it's the same thing, okay? That you are flipping the molecule, okay, from one state to another, from one configuration to another. So that is SN2 mechanism. Any questions at this point about SN2? Okay. Now let's look at SN1. Okay, SN1 is now substitution nucleophilic first order. Okay, so in case of SN1, we have a little bit different kind of a substrate. This is the reaction you did in the lab already. So in this case, and I generally tend to write things on my arrow a lot, and I'll explain that also. This is what we have. So you still have the substrate, you still have the nucleophile, still have the product, and you still have the leaving group. Okay, so none of that has changed. The rate, however, has changed, and now the rate of reaction can be written as this. So which means that only the substrate is involved, okay, in the rate here, which means only the substrate is involved in the mechanism, okay, over here. So that is the key thing here. The nucleophile is not even in the picture for the rate of reaction. The order is 1. So this is first order reaction. And this is with respect to the substrate. The nucleophile is not in the picture. It means it tells me in the mechanism that I have to write, I cannot involve the nucleophile because it's not in the rate equation. So this is how the mechanism works for SN1. Here, the chloride is going to leave first. Okay, so the chlorine leaves, that's the leaving group, and then you end up getting what's called the carbocation. And a carbocation, remember, is the positive charge on the carbon. Once this intermediate is formed, and this is the transition state or the intermediate, and I'll tell you the difference between the two. Now you have the nucleophile coming in. There is again a lot to unpack over here, okay, regarding this whole thing that happened. But let me go ahead and draw the graph first, okay, and then we'll talk about the intermediate or the transition state. So in this case, you actually have 2 steps going on. Even though it's a first order reaction, or because it's a first order reaction, you have 2 steps. In one step, you have the chlorine leaving. In another step, you have the nucleophile attacking. So it means that your transition state is going to have 2 curves. You have the first one, and then you have the second one. Generally, the second one is the faster of the steps. So the first step requires a higher amount of activation energy. The second one, not so much. So it's the faster one. So the first step is the rate determining step, because that's the slower one. Okay, so this question goes out to Shams. So I hope you're here, Shams. What is the hybridization on this carbon? Don't write it on the chat because I can't see the chat. So Shams, are you here today? I guess he's not here today. Of course, because I'm calling out on him. So after Shams is Nicole. Nicole, you are here?
Yes.
Yes. So what is the hybridization on that carbocation?
R.
Not the RNS, hybridization. SP, SP2, SP3.
Oh, I'm sorry. It's SP2.
SP2. Sure?
I believe so.
Very good. I'm so glad you held your ground. Okay, so SP2. Okay, SP2 is the hybridization. Now think about all the things that go with SP2 hybridization, which is that you have a 120-degree bond angle and you have a trigonal planar structure. Okay, so in a trigonal planar structure, which is just like a flat thing, the nucleophile can come from this side or it can come from this side, which means that the resulting compound that you form, this one doesn't even have a chiral center because you have two methyl groups, but it's actually going to be a racemic mixture. This is possibly one of the most important things. I mean, after all, SN1, SN2, that's important too. But the stereochemistry, especially if you're generating a chiral center, this is the most important thing for SN1, SN2, is to see which one is going to give you a mixture, which one is going to give you a pure compound, because it makes so much difference in the mechanism of the reaction, okay? So the carbocation that you're forming here, that is the one that gives it the racemic mixture, because you're talking about something that is planar, okay? So I'm gonna come out for just a second here, because I want to show you how this works. Okay, so if you have a tetrahedral, okay, so if you have a tetrahedral like this, okay, and you're trying to do a reaction, oh, first of all, here's your leaving group. Okay, let's look at this one. Here's the leaving group, and this is for SN2 reactions. So if this is your leaving group, what I was talking about before is that if you have any kind of nucleophile coming in, your nucleophile is not going to come from here because there's already something over here. It can only come from behind where there is nothing. So it's almost like exactly the opposite space, okay, of the leaving group. That's where the nucleophile is going to come. That is an SN2. In case of an SN1, what happened is that this is gone. Okay, so the the leaving group is gone already. So once that is gone, if I look at it this way, and you're thinking about two-dimensional, then, well, that's a trigonal planar. So if this is trigonal planar, the nucleophile can come from behind or it can come from the front. It doesn't really matter, okay, because now there is room on both sides. In case of SN2, there is no room on this side, okay, so it has to come from behind, okay, the nucleophile. So this is an important aspect of SN1, SN2. This is the basics. What we will do on Thursday, because I have to talk about the exam now, yeah, I remember it usually when I tell you to remember, I remember, is we're going to talk about what determines if it's going SN1 or SN2. So if you want to take a look at your PowerPoint study, let me know, do you think there is anything in there that you are not able to do, or were you able to handle everything in there? The only one you may not have been able to do maybe is the stronger nucleophile. Were you able to do that? Question number 3. Was that okay?
Professor,
Mm-hmm.
the alkyl nomenclature is due today, right?
Yeah, and the SN2 also is due today. There are 2
Oh.
things due today. Yeah. So that's why I'm asking if there was anything in the SN2 now, because alkyl halide nomenclature, I think that was not so hard, but this is the new stuff. So in the SN2, I asked you about which one is the stronger nucleophile. So if you were not able to do that, think in terms of bases, okay, which what we did in chapter 3 is which one is a stronger base. Think in those terms and then do your best, okay, for that. And then we'll see, okay, what is missing in there. Is there anything that you would like me to go over in the PowerPoint study?
Yeah, I have a question. 4. So for question number 3, it's about boiling point. Is there a pattern that we can use to tell what's the highest boiling point?
For question number 3 for the alkyl halide nomenclature?
Yeah.
Yeah. So generally for the boiling point, you want to see what are you comparing, you know, and generally in this case for halogens, it's going to be the molecular weight.
Okay.
Okay? Yeah.
Thanks.
Okay. Anything else? No. Okay. Well, as you are doing the SN2, I know you don't have to submit the SN1, but do it today. Okay, do the SN1 today also, and it's made very similar to SN2. And the reason I want you to do it together is because you can see the differences between the two, okay, in there. So it will help you to understand, okay, how those two are different, okay, from each other. Other than that, I think that should be good for today. So I'm actually opening your exam right now. So that's why you see me a little distracted here. Okay. Because there were a couple questions in here that were, it's something that I need to talk about, okay, so that you don't make those mistakes again, because there were not that many questions that actually stood out. A lot of you were just like here and there. So most of it was fine. There's not much of an issue. The one thing that was an issue was finding the longest chain, okay? That was one of the issues. And so what you had to do, there was this one in which you had, let me come back to the Zoom thing here. 1 second. Okay. There. So there was one question which went something like, it was this long chain here and then don't know how it went, but it was something like this, okay? And so it was really ridiculous looking compound. So I think what we were having a hard time with was naming this one, okay? So this is 1, 2, 3. This compound or this substituent would be called 1-methyl, and then because it's 3 carbons, it would be propyl. I think you had a butyl in there. But here is the important part. You need to put everything in brackets, and then you need to tell exactly where it is. So this is 1, 2, 3, 4. So you have to put a 4 in front of it. Generally, when you type out your answers, it has to be absolutely correct for it to give you credit. Okay, so if you miss a bracket, then you lost points. If you miss a dash, you lose points. Okay, which is really how it should be. I just don't have the heart to do it. Okay, so when you write your answers to me, I just circle it and I let it go. But computer is not like that. Computer is really very strict, okay, in grading. So I think this is the only one that was written for grading, okay, for the computer. But that's kind of what happened, okay, in that. Alia, yes.
Is there any way that when we're taking the exam, we don't have to submit each answer manually, or like if we save our answers, if the exam time runs out, like it won't mark it wrong if we haven't submitted it? I don't know if that's making sense.
So what you're trying to tell me is that as you're doing the exam, you have to submit each answer before you can go to the next one?
You don't have to submit it in order to go to the next one, but in order for it to be turned in, you have to press submit. And so like sometimes, like for this one, say I didn't remember the bracket and I want to get back to it, I don't want to spend too much time, I would save the answer and then I'd finish the rest of my exam. But if I forgot, it would mark you wrong because you never submitted it, but you saved it and it's answered.
So
but sometimes it's a lot of stress to submit the answer.
Okay, so tell me another thing then. Do you have to submit the exam as a whole, or do you have to submit each question?
You have to submit it by each question.
You have to submit by each, okay. So I think the best thing to do is, if you're not sure of any question, Well, you need to sit with a piece of paper then. Okay, I'll see if I can change the settings, although I don't think I can, not for that one. Okay, not for how that submission takes place. I'll see if I can for yourself what you need to go back and look into. Okay.
At least like if we save our answers and it's been answered, like sometimes it'll mark it wrong. And so like it may just be easier if I've saved it and I'm not sure and I'll get back to it at a time. But if I don't get back to it, like it is as it is. Yeah.
So there are two buttons there, save and submit.
Yeah. And you either have to submit and you can't change it, even if you think about it later, or you save it and you have to manually go back, which you may run out of time.
Okay, all right. I'm gonna see if there's anything I can do to change the, you know, how you are answering. I have a feeling I don't have a lot of freedom. Okay, so Wiley Plus doesn't allow too much of manipulation, but I'll see if I can, okay?
Okay, thank you.
Otherwise, yeah, sit with a piece of paper so you can write it down. That's, for now, that's the best I can say. So this question, the other question that was wrong, yes, one is the hard one. It is kind of drawing your relation at the so the other one had was model, and the CL, and there's CHP. And if you're looking at from here, you draw the dimension. You can also do this by looking at, huh?
Professor, you were going in and out.
I am going in and out. Okay. Well, ask me that.
Oh, now you're muted.
Yeah. So that one and the other one, that was the relationship between two molecules. Most of it was the relationship between two molecules. Actually, you know, is this, where you had two molecules, and in the two molecules, it was like here's this, so whatever, and then the other one was there's a relationship between each two that says arcs on both sides. So if one will have to be the front, and the other one will be the back, this has to be in the universe. Okay, there's a relationship. That line was like this, and that was the universe. So so how was that? And I don't know if you're looking at my screen or not now. And you see, okay. Now